Now, I actually snuck something important in here. I actually snuck two things that are important in here. The first is what's called the Markovian property. Do you remember what the Markovian property is, Michael?
From what?
From, I don't know. Actually, where does the Markovian property come from?
I'm going to say Russia.
Okay, yeah, from the Russian.
Yeah, so I have Russian ancestors, and they passed on to me this idea that Markov means that you don't have to condition on anything past the most recent state.
That's exactly right. The Markovian property is that only the present matters.
And they had to pass that down to me, one generation at a time because, Markov property.
That's exactly right. That was very good, Michael. So what does this mean? What this means is our transition function, which tells you the probability you end up in some state S prime, given that you were in state S and took action A, only depends upon the current state S. If it also depended upon where you were 20 minutes before then, you would have to have more S's here, and then you would be violating the Markovian property.
So is this do historians hate this?
Well, one never learns anything from history.
No, you're supposed to learn from history or you're doomed to, I don't know, let me make something up. Repeat it.
Fair enough. Historians probably don't like this, but there is a way for mathematicians to convince them that they're okay with it. And the way that mathematicians convince you that you're okay with it is to point out that you can turn almost anything into a Markovian process by simply making certain that your current state remembers everything you need to remember from the past.
I see.
So in general, even if something isn't really Markovian, you need to know not only what you're doing now, but what you were doing 5 minutes ago. You could just turn your current state into what you're doing now and what you were doing 5 minutes ago. The obvious problem with that, of course, is that if you have to remember everything from the beginning of time, you're only going to see every state once, and it's going to be very difficult to learn anything. But that Markovian property turns out to be important, and it actually allows us to solve these problems in a tractable way. But I snuck in something else, Michael. What I snuck in is this idea about the transition model is that nothing ever changes. So
Nice.
The second property that matters for Markov decision processes, at least for the sets of things that we're going to be talking about in the beginning, is that things are stationary. That is, for the purposes of this discussion, it means that these rules don't change over time. That's one notion of stationary. Okay?
Does that mean that the agent can never leave the start state?
No, the agent can leave the start state anytime it takes the action that gets it out of the start state.
How is it stationary then?
It's not stationary. The world is stationary. The transition model is stationary. The physics are stationary. The rules don't change on you.
The rules don't change.
Right.
Okay, I see.
There's another notion of stationary that we'll see a little bit later. Okay, last thing to point out about the definition of a Markov decision process is the notion of reward. So reward is simply a scalar value that you get for being in a state. So for example, we might say, this green goal is a really good goal. And so if you get there, we're going to give you $1. This red goal, on the other hand, is a very, very bad state. We don't want you to end there. And so if you end up there, we're going to take away $1 from you.
What if I don't have $1?
Someone will give you the $1. The universe will give you the $1. Or
and then take it away.
The universe will take it away. Even if you don't have it. You'll have negative dollars.
Oh, man.
Okay, so reward is very important here in a couple of ways. Reward is one of the things that, as I'm always harping on, encompasses our domain knowledge. So the reward you get for an estate tells you the usefulness of entering into that state. Now, I wrote out 3 different definitions of R here because sometimes it's very useful to think about them differently. I've been talking about the reward you get for entering into the state, but there's also a notion of reward that you get for entering into a state and taking an action. There's a reward, or being in a state and taking an action. There's a reward that you could get for being in a state, taking an action, and then ending up in another state S prime. It turns out these are all mathematically equivalent, but often it's easier to think about one form or the other. But for the purposes of for the rest of this discussion, really you can just focus on this one, the reward or the value of entering into a state. And those 4 things by themselves, along with this Markov property and non-stationarity, defines what's called a Markov decision process, or an MDP. Got it?
I'm a little stuck on how those could be mathematically equivalent.
Well, we'll get to that later. Do you like a little bit of intuition?
Sure.
Well, you can imagine that just as before we were dealing with the notion of making a non-Markovian thing Markovian by putting a little bit of history into your state, you can always fold in the action that you took to be in a state, or the action that you took to get to a state as a part of your state.
But that would be a different Markov decision process.
It would, but they would work out to have the same solution.
Oh, I see.